All right, here we are at the very last section of the textbook that we're going to cover in Calculus 1. This is something that we call the substitution rule. To get into it, we have now looked at integrals all throughout Chapter 5. And as of Section 5.3, we've come up with an effective way of evaluating them. 5.4, we introduced indefinite integrals. So we are now dealing with indefinite and definite integrals, and we can evaluate them using antiderivatives. However, there's a problem there. The problem is that the overwhelming majority of functions that we're going to be asked to integrate throughout Calculus 2 and onward are not, it's not obvious what their antiderivative is. It has to be a function that's relatively simple, like a polynomial or something like that, or a function where it just so happens to be the exact derivative of a function that we already know about. So if you see a secant squared in there, for example, you know that its antiderivative would be tangent of x plus c. But how do you deal with something like this? If I want to integrate 2x of cosine of x squared, and I'm actually going to put this in parentheses, how do you integrate that? Well, that doesn't look like any of the functions that we've dealt with so far as finding antiderivatives is concerned. So we need something more. We need more flexibility in how we can handle these things. And what we're going to talk about now, the substitution rule, it's also known as U-Substitution. That's typically what I would be calling it. We're going to see. This is going to be one of many different integration techniques that you can learn. In Calculus 2, you spend a whole lot of time talking about different integration techniques, but I would argue that this one is actually the most important one. It's the one you're probably going to end up using the most, and even when you learn those other techniques in Calculus 2, you're oftentimes using them in conjunction with this. So this is an extremely important rule in our technique for evaluating derivatives, and it's going to open the door to a whole lot more I think I said derivatives before, I meant to say integrals. It's going to open the door to a whole lot more integrals that you're able to evaluate. So let's talk about what this rule is, where it comes from, and then let's do some examples. So the U-Substitution or the substitution rule is basically the integral counterpart of the chain rule. It works because of the chain rule. So as a reminder, if you're differentiating f of g of x, assuming that f and g are both differentiable, by the chain rule, that's equal to f prime of g of x times g prime of x. So here's a function, f of g of x, and here is its derivative, which means f of g of x is the antiderivative of this expression right here. Or using indefinite integral notation, the indefinite integral of f prime of g of x times g prime of x dx equals f of g of x. Now looking at this looks really complicated, so we tend to simplify this notation. If I set u equal to g of x, then I can substitute a u in for the g of x here and the g of x here. And then I'm going to define du to be the derivative of g of x times dx, that differential dx here. So this g prime of x dx is going to be replaced with a du, and this whole thing simplifies down to this. F prime of u du equals f of u. And what this is a variable substitution. We're taking part of our original integrand and defining part of it to be equal to this variable u, then changing all of the other parts accordingly to make the integration easier to handle. And that gives us this thing here that we call the substitution rule. Okay? This is just restating what I already stated there. So once again, here's that one integral that we introduced, or that we started the section off with. How do you evaluate this using the substitution rule? The substitution rule starts with you deciding what part of this function you're going to label with a u. And there's not a universal way of deciding what you should call u. But one of the first things you want to look for is any function that appears to be inside another function. Remember, u is taking the role of g of x, and g of x is the inner function in this composite function right here. So here I have a composite function, cosine of x squared. X squared is inside the parentheses there, which suggests I should probably try setting u equal to x squared. Okay, so now we said that if we set u equal to g of x, then we're going to define du to equal g prime of x dx. So as soon as I choose a u, I then need to show what du is equal to. Du is equal to the derivative of u, which would be 2x. Then there's a dx that makes an appearance as well. Well, if you noticed, the 2x dx shows up in my integral. It's part of my integrand, right? So I can rewrite this integral as cosine of u, because x squared we defined to be u, and then everything else, the 2x and the dx together, is equal to du. And if you notice, I now have a much simpler looking integral that I know how to evaluate. What is the antiderivative here? What is the indefinite integral of cosine of u? Well, it would be sine of u plus, sort of write an equal sign there, plus c. Okay? Now, I'm not really done because I don't want to leave things in terms of u. My original function that I was integrating was in terms of x. So I need to substitute back this x squared for the u here. And this is equal to sine of x squared plus c. Okay? This is the antiderivative that I was looking for. It's the indefinite integral of this function. And if you want to verify, remember, you can always verify that you got an antiderivative correct by taking the derivative of your answer and seeing that it gives you your integrand back. I'll let you do the check. It's pretty easy with this one. It's just the chain rule. Okay? That's how U-substitution works. Here's another example. Okay? I want to integrate x times the square root of 1 minus x squared. So as before, we have to begin by deciding what part of this function we want to call u, and then seeing if du makes a natural appearance in the rest of that integrand. So using the same suggestion as the previous example, look for a function that appears to be inside another function. This 1 minus x squared is inside that radical, which suggests to me that we should set u equal to 1 minus x squared. Okay? Now, that would mean that du is equal to negative 2x dx, the derivative of u, and then we include the dx in there. Okay? Now, if you notice, I have some of that appearing. I have an x dx here, which is great, but that negative 2 that's appearing here is not making an appearance anywhere in here. So how do we deal with that negative 2? Well, what I need is for this right-hand side to exactly match this stuff, x and dx. And I can, this is an equation. I can do algebra on this. I can multiply both sides by negative 1/2, which gives me this, negative 1/2 du equals x dx. Notice now that the x and the dx here together, I can swap those out for a negative 1/2 du. Now my integral can be written this way. The integral of the square root of u, let's write that as u to the 1/2 power. Then I have negative 1/2 du, which I can substitute in for the rest of that stuff in that integral. The negative 1/2 being a constant can actually be pulled out of the integral because we have that property of integrals. The du is going to have to stay put. But now let's take a look at what we have. Negative 1/2, I'm going to integrate this, add 1 to your exponent, which would give me 3/2, and then divide by 3/2, same thing as multiplying by 2/3, plus c. This is equal to, when I multiply these fractions, negative 1/3 u to the 3/2 power, which is 1 minus x squared to the 3/2 power plus c. This is my answer. Okay? So as was the case In the previous example, it's a good idea to verify that you did this correctly by taking the derivative of your answer and showing that the integrand, the result is your original integrand. And again, I'm going to leave all of those checks to you, but I encourage you to do it as you're following along with these examples. Here's another one. We want to evaluate the integral of sine of 1 over x squared dx. Okay? So once again, I'm going to try and take that same advice as before, where I'm looking for a function that appears to be inside another function. And the function 1 over x is appearing inside the sine function there, which to me suggests that we should set u equal to 1 over x. And if that's the case, then du is going to equal negative 1 over x squared. That would be the derivative of that guy, dx. If you notice, I have a 1 over x squared in here. It's being multiplied to the sine of 1 over x. But the negative is not accounted for. And that's, again, not really a problem. Multiply both sides of this by negative 1. So I have negative du equals 1 over x squared dx. Now, the 1 over x squared is already in the integrand, and the dx is in there. It's always in there. So I have enough stuff here to substitute things out. This is the same thing as the integral of sine of u times negative du, because that's what the rest of that stuff is. It's negative du. Let's bring the negative out. Okay, this is equal to negative. Remember, the integral of sine of u would be negative cosine of u plus c. The negatives will cancel each other out, and then we substitute 1 over x in for the u to get everything back in terms of x. Okay? There you go. Sip some of my coffee here. Okay. Those first three examples, even though they're more involved than the kind of integrals that we've evaluated so far using antiderivatives, those are really the easier ones, because the choice of u was a little bit obvious in those cases, because there was a function that appeared on the inside of another function. U substitutions are not always so obvious. This example is not quite as obvious. We want to evaluate the integral of x over 1 plus x to the 4th power here. And it's not immediately obvious what we should choose u to be. For example, if I set u equal to x to the 4th, then du is going to be 4x cubed. But I don't have any x cubed showing up anywhere. If I set u equal to x, then du would just equal 1 times dx. And I'm missing all of this stuff down here. So how should we choose u? Well, in this one, I'm going to rewrite my integral as x over 1 plus x squared squared, because that's the same thing as x to the 4th. And by doing that, I've created an inside function, that x squared there. I'm going to set u equal to x squared, which would make du equal to 2x dx. Now, notice the x dx is appearing in my integrand, and the 2 is the only thing that's not appearing, but that's an easy fix, as we've seen before. Okay, it becomes 1/2 du. So now let's rewrite this integral. The x dx is going to become du. And the x squared becomes u, so this becomes 1 plus u squared. Now I put my du up here, but I've mentioned this before, I could also bring it out here and just put a 1 up there. 1 over 1 plus u squared du is the same thing as what we have written here. Do I know an antiderivative for this? I do, because 1 over 1 plus u squared has an antiderivative of arc tangent. This is equal to arctan of u plus c. And then I can substitute my x squared back in for u. Arctan of x squared plus c. Okay? And that would be my answer. That would be my integral. Hopefully, as we're doing more and more of these, this is starting to make sense. Okay, here's another one that looks very similar to one we've already done. We've done that one that had a radical in it. And we're going to make this same sort of, we're going to use the same strategy, I should say, when choosing u. But it's going to involve a little bit more work than you might initially expect. So I'm going to look at this thing and I see that 2 plus x is inside that radical, which suggests that I should set u equal to 2 plus x. Okay? But that would mean that du is just dx, because the derivative of this is 1 times dx is just dx. So I have the square root of u appearing here, and I have a dx, which I'm going to swap out for a du, but what am I supposed to do with this x squared right here? Well, sometimes when we do a u-substitution, you have to go back to the original substitution that you made and do a little algebra with that. Notice if I solve this for x, I get x equals u minus 2, okay? And there's an x squared appearing in my integrand. I would like to swap that out for an expression in terms of u. So that means if I wanted to see what x squared looked like in terms of u, I would be squaring both sides of this. This implies that x squared equals u minus 2 squared, or u squared minus 4u plus 4 after expanding. So this is telling me how to rewrite my integrand. X squared becomes that. U squared minus 4u plus 4. Then I have the square root of u, because that's what I made my u substitution. I chose 2 plus x to be u. So that becomes u to the 1/2 power if I'm going to use rational exponents. And then the dx is just going to become du. Okay? Now it's still a complicated looking integrand, but very doable, because if I distribute that u to the 1/2 in, this is the same thing as the integral of u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 power. And I could just use my power rule in reverse to find all of these antiderivatives. I would get 2/7 u to the 7/2 minus 8/3. Or actually, no, I'm sorry, that's not 8/3. 8/5 u to the 5/2. Make sure that's right. Yeah, that would be right. Plus, what is this? It's going to be 3/2. It's going to be 8/3 right there. U to the 3/2 plus c. Okay, and then finally swap all of your u's out for 2 plus x's. So this is equal to 2/7 times 2 plus x to the 7/2 minus 8/5 times 2 plus x to the 5/2 plus 8/3 times 2 plus x to the 3/2 plus c. Okay, and I could factor like a 2 plus x to the 3/2 power out and try to simplify things. I'm not really worried about doing that with this example, because the point was to show what our strategy was for choosing our u there. So a lot of the times these integrals come out to something rather complicated looking like this, but hopefully you're seeing what the work looked like for that. And again, this one was a little tricky, because in order to get that x squared up here into the form of something that only involved u, I had to solve this original equation for x and then square it to figure out what x squared looked like in terms of u. But that ultimately did it for this problem. Okay, let's go ahead and stop this video here, and I think we might be able to finish this section out in part 2.